Hi again, I'm Molly Campbell, science writer and editor for Technology Networks, and I'm here to introduce our next talk. High-speed, untargeted 4D lipidomics LC-MS workflows with parallel accumulation serial fragmentation, or PASEF. I'm pleased to have Dr. Lucy Woods joining us as your presenter for this talk. Lucy has been working for Bruker Daltonics for more than 5 years, prior to which she worked for pharma companies GlaxoSmithKline and AstraZeneca, developing workflows to identify unknown impurities using mass spectrometry. Lucy has a strong background in ion mobility mass spectrometry, having completed her PhD under the supervision of this year's Thompson Medal winner, Professor Alison Ashcroft at the University of Leeds. This led Lucy to join Bruker and take the role of product manager for the timsToF series, where she was responsible for launching the timsToF Pro and timsToF Flex platforms. This year, Lucy takes on a new role as Global Business Unit Manager for Phenomics and Metabolomics, where she is responsible for the development and execution of new workflows for metabolomics and lipidomics using the timsToF platforms. A very warm welcome to you, Dr. Woods. Following the presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A tab. Please be aware that you can ask questions at any time during the presentation, and we will cover as many as possible at the end of the talk. The Q&A session is your opportunity to tap into Dr. Wood's expertise, so I very much encourage you to ask questions. If you experience any technical issues during the presentation, please do let us know using the chat button feature. I will now hand over to Dr. Woods.
Okay, so thank you, Molly, for the kind introduction. So in the presentation today, I'm going to show you how the timsToF Pro can be used in a high throughput, high sensitivity lipidomics workflow. And in this, we utilize an additional dimension of separation, which gives you more confidence in your lipid annotation. So in this workflow, we utilize the timsToF Pro. Now, the timsToF Pro uses trapped ion mobility spectrometry, which is also known as TIMS, and this can be used to further characterize compounds. Now, in TIMS, we introduce ions from a capillary, and we deflect them by 90 degrees and introduce them into the TIMS funnel. They're deflected by 90 degrees, and the ions are all trapped within this section here, which is called Analyzer 1. Now, once the ions are transferred to the second analyzer, then they are organized based on their mobility. So here you can see there are ions of 3 different sizes, 3 different shapes, and therefore they have different mobilities. So this larger ion shown here is pushed further into this analyzer section by the inflow of gas from the source. And this smaller ion is trapped regionally in a different position in this second analyzer. Now, these are trapped by an electric field, which we can control and decrease. And as we decrease them, these ions are selectively eluted based on their mobility values. Now, this is something that we call time focusing, as we pre-concentrate these ions within the analyzer, and we then selectively elute them based on their mobility. So we end up with these tight packets of ions, which are around 5 milliseconds for each of the ions of each mobility. And by separating ions based on their mobility, we are also able to record what's called their collisional cross-section, or their CCS. And this is a property of an ion which is independent of the way that the ion's been introduced into the mass spec. And you can use this to further characterize this ion and give you additional confidence into its identification. Now, the reproducibility of CCS values has been analyzed numerous times. And on this slide here, you can see a study in which we analyzed the CCS reproducibility at 2 different sites, so based in Bremen and based in Munich. And what's particularly nice about this study is that the lipids were introduced using 2 different types of chromatography. So in the Bremen site, a high-flow UHPLC method was used. And in the Munich site, so this was performed at the Max Planck Institute in Munich. And here they introduced the lipids using a nano-flow method. And despite the 2 different methods of sample introduction, you can see here that for these different lipid classes, we have a very high reproducibility of CCS values. And furthermore, if you look not just at the reproducibility between the systems, but between the different injections shown here on the right, then you can see a very high reproducibility. So from this scale, the lowest value that's plotted has a correlation coefficient of 0.991. So for each of these injections on each of these 4 different systems, we experience very stable CCS values. And this shows you that libraries of CCS values are able to be created to give you additional confidence in the annotation of your compound. And libraries can be both measured or they can be compiled from existing databases. And there's been a number of publications recently in which the CCS values for a range of different compounds has been measured and is now available. So this top figure here shows you where the CCS values for different lipids have been acquired using different methods and different instrumentation. So this is by the group, Professor Zhu's group in Shanghai and Professor McLean's group in Vanderbilt. And despite 2 different methods of mobility separation being used, the agreement between these values and the TIMS values is very high. So they're always within 2%. And this really shows you that wide scale sharing of CCS libraries can be employed. Now, as well as seeing an increase in CCS libraries, we're also seeing a large increase in CCS prediction. So here on the bottom, we employed a CCS prediction model to see if we can predict different lipid CCS values. And again, you see the reproducibility is very good. So between the values that are measured using TIMS and those which can be predicted, you have a typical error of less than 2%. And this particular CCS prediction model has been incorporated within our processing pipeline, so within our software Metaboscape. So you're able to use this as part of your standard workflow. And I'm going to show some examples on this later on in the presentation where we've used this to confirm the identification of a biologically relevant lipid. Now, as well as obtaining accurate CCS values for your compound, you can also use TIMS to actually separate out different lipid classes. So here you can see 2 different lipid classes, the PE lipid class and the PC lipid class, and these differ in mass by just 38 millidaltons. So if you look on the mass axis alone, they are very difficult to differentiate, and they especially will not be differentiated if you isolate them on a quadrupole. However, these 2 lipid classes have different mobility values. You can see this plotted here with the mobility on the y-axis. And because these 2 lipid classes have 2 different mobility values, then we elute them at different times from the TIMS analyzer. And because of this, we fragment them separately. So we're able to record these clean MS-MS spectra with these characteristic ions here for the PE neutral loss, and here for the PC lipid class. And this gives us additional confidence in the identification of these different lipids. So these 2 aspects are the main fundamentals of the 4D lipidomics workflows, having clean MS-MS spectra and reproducible CCS. So I'd like to show you how this workflow can be employed for the analysis of biological samples. And in this case, we're looking at C. elegans as an example. So C. elegans is a model organism which can be used to study aging. And in this particular study, we compared the wild type C. elegans to a DAF2 gene mutant. And the DAF2 mutant is one which is known to regulate the rate of aging. So here we wanted to see what the differences in the lipidomics profiles of these 2 strains were. Now here you can see the base peak chromatogram for this sample. So for the C. elegans, you can see it's an extremely complex sample which is composed of a number of lipids. And if we look at this in more detail, so here we can plot the LC separation, and we can plot it versus the intensity of these features which are being detected within the C. elegans. Now with PASEF, we fragment much faster than with any other fragmentation method. So each one of these spheres here, each one of these bubbles shows you where, not just where a feature has been detected, but where it's been fragmented, and we've recorded MS-MS spectra. So not only can you see the large number of MS-MS spectra that are being acquired in a single LC run, but you can also see that this covers a wide dynamic range, so 4 orders of dynamic range. So as well as acquiring more than 10 times more MS-MS than in a standard DDA approach, we are also able to spend more time generating better quality MS-MS spectra. So each of these ions are fragmented more than once. So on average, it's 1.6 times. And this way, the low abundant ions can be fragmented multiple times, so we obtain better quality MS-MS spectra. Now you can see this in a bit more detail. So if we look again at the base peak chromatogram and zoom in on one of these tiny peaks here. If we look on in the mass spectrum itself, then we can see that there's this lipid present or signal present at mass charge 664, and this diamond on top here shows you that it has a fragment spectrum. So this ion at 664 is 10,000 times lower than the main peak within the base peak chromatogram. But it was fragmented and you get clean MS-MS spectra, so you're able to see distinctive neutral losses and assign an identification for this lipid. So within this workflow, once you've acquired the data, you need to be able to process it and identify these lipids. And we do this in our software called Metaboscape. So I'm going to briefly run through what the workflow here is. So after the acquisition of the data, the first thing we need to do is peak pick the data. And this is done using our T-Rex algorithm. So in this case, it's T-Rex 4D, because we consider features based on the mass to charge, their intensity, the retention time, and also the CCS value. Now, one nice feature of T-Rex 4D is that the first analysis of all of these features will look at features which are present above a certain threshold. So if you have a sample set of, say, 4 different sample types here, then it may be that one feature has a lower abundance in one of the samples than in the other 3. Now, using a standard peak picker, this peak would just display as a 0 value, as you can see in this table here. But using T-Rex 4D, the algorithm will go back through the data and will lower the threshold and do a second pass for such features that are present in numerous samples and missing in a small few. So with this, you can see that this feature has been assigned an area, and you can now confidently look at the differences in abundances between these different samples. And the second part of the T-Rex feature finder is that the algorithm will look for adducts and for neutral losses, which all belong to the same compound. So here you can see an example where you observe the protonated, the sodiated, and the potassium adduct, as well as the neutral loss for one single compound. And these are all grouped together in one single entry in the table. And what's nice is that for each one of these adducts, you record a CCS value. So you can use this to give you additional confidence in your ID. And for the annotation to give a lipid annotation to each of these compounds, the way that we do it is using what we call an annotation quality scoring. So with this, we'll look at the accurate mass for each of the compounds. We'll look at the retention time for each of the compounds, the isotopic pattern, the MS-MS score, and also the deviation in CCS value, where you have a library value to compare it to. So we'll look at each of these 5 attributes so that we can confidently say that where there is a high match, then this is a highly confident annotation. Now you might wonder what these 2 bars here. So here we have a high confidence window where if you match it, the software will display 2 different bars, and a low confidence window where if in this example for retention time, the match is within a wider threshold, then it will just display a single bar. And in the latest version of the software, we have a new annotation tool for lipids in particular. So here we have a rule-based annotation where the software will search through the fragment spectra and will assign the lipid chain composition based on the fatty acid chain fragments which are observed, and also the lipid class based on the head group and on the water loss. Now, these rules have been assigned based on the proposals from the Lipid Standard initiatives, and these annotations will help you reduce the number of false positives which are observed within your data. Now, with this, we've also brought a new visualization. So with the four-dimensional data, there are a large number of attributes that you can look at for each one of your compounds. And if you look here, we plotted master charge versus CCS, and these different colors shown here are different lipid classes. So you can quite clearly see where different lipid classes cluster depending on their different retention times and on their different master charge. Now, you can also see the different CCS values that these different lipid classes populate. And if we look at this in more detail, and if we look at a single lipid class, so in this case, the TG lipid class, then what we can see is we get this very reliable increase in CCS as we increase the chain lengths. So it makes sense that as you add CH2 groups to your chain length, you get a linear increase in the CCS value. And the same for when you increase the number of double bonds, you get a decrease in the CCS values. So you can use these views to give you, to help you spot false positives and to show where an annotation may have been missed within the data set. And we've also expanded this to include Kendrick mass defect views. So if you plot the master charge versus the Kendrick mass defect, then you see clustering of lipids according to their different lipid classes. So here, for example, you can see these TG lipids that we showed here based on their CCS. And you can see, again, this pattern of TGs depending on the number of the chain length as well as on the number of double bonds. You can also see here the LPCs cluster, so they have quite a distinct master charge. And you can see from this bubble size here, this shows you the CCS value. So you can see the LPCs have a much smaller CCS value than, for example, for TGs. Now, within the Metabolomics software, we also have a number of statistical tools. So if we look more closely at the difference between the two different types, the two different groups, so between the wild type group and the DAF2 mutant, as well as a QC group, then we can see that there's a clustering of each one of these variants. And if we look in more detail at a single lipid that differs significantly between the different groups, then we can see that for this particular signal, there is a large difference in the intensity between the QC group, between the wild type, and between the DAF2 mutant. Now, you can see this difference in abundance, and you can see that this is the same lipid signature in the different types by comparing the retention time, which is near identical for this feature across the different groups, as well as for the CCS values. So we have a very stable CCS value that you can compare. Now, for lipidomics analysis, it's particularly important that we are able to combine positive and negative data, which we can do within Metabolomics. So for positive data, we get information on this, on the head group, so that we can assign the lipid class. And for the negative data, we get the characteristic side chain fragments. So within Metabolomics, we can merge these data sets and analyze them together. And we can see from this that the identification of this lipid is in fact a PC2525 lipid. And if we go back to this prediction algorithm that I mentioned has been incorporated into our software, then we can feed this structure in. And from this structure, we can calculate a CCS value. So once we compare that to the CCS value that's measured, this gives us additional confidence that we're able to assign this, this chain composition to this lipid based on the CCS values. So this is the workflow as it is at the moment. We are seeing a trend in the field for increasing the throughput of analysis. So with PASEF, we're able to obtain more MS spectra in a shorter time. So we've ran SRM 1950, mouse liver, and HeLa cells through our 4D-Lipidomics workflow. And we found that we always obtain more than 65% of the features with MS-MS spectra, enabling us to give more confident lipid IDs. And we can use this, this increasing speed of acquiring MS-MS to shorten our LC gradient. So whereas we started off looking at 20-minute runs, we can shorten the gradient all the way down to 6 minutes and still obtain a high number of lipid IDs due to this very fast MS-MS acquisition rate. And in the future, we look to expand this further. So we look to increase the throughput by interfacing the EvoSep1 to the timsToF system. So this has already been done for Proteomics, and we're now using this workflow for 4D-Lipidomics. And with this, we want to further increase the throughput as well as the robustness of the workflow. So with the EvoSep1, we can reduce the overhead time to less than 3 minutes whilst maintaining the sensitivity. And there's been some preliminary data that was presented at ASMS, which shows that with the EvoSep1, we get a very good reproducibility in the retention time values, as well as a very good stability between different lipid classes. So here you can see different time points for the analysis of different samples and the distribution of different lipid classes which are observed from the analysis. So this stays pretty stable throughout the 30-hour time points. And in addition, if you look at the intensity, so the abundances of each of these lipid classes, then this also remains stable. So this is where we see the workflow heading in the future. So I'd like to thank everyone who helped with the acquisition of this data, not just at Bruker, but with our partners as well. So everyone at the Max Planck Institute and at EvoSep who are helping with the high throughput measurements. At the Helmholtz Center, I'd like to thank Mikhail Witting and Philip Schmidt-Copeland for providing the elegans sample. And at Mannheim Technical University, the group of Carsten Hupf and Christian Marsching for helping with the development of the 4D-Lipidomics workflow. So with that, I'd like to thank you and ask if there's any questions.
Thank you very much, Dr. Woods. That was an absolutely fantastic talk. So I know that we are going to have lots of questions and we don't have a lot of time. So we'll move straight on to the Q&A session now to try and cover as many questions as possible. So the first question that we have is, when it comes to lipidomics analysis, what is the major advantage to using IMS in your opinion?
So I think the two main advantages are the reproducible CCS and the clean MS and MS-MS spectra. For lipidomics analysis, I would say it's the clean MS-MS spectra, because if you don't have this mobility separation, then you'll always see co-isolation of lipid classes such as PC and PE lipids, and you will always see chimeric spectra.
Thank you, Dr. Woods. So the next question that we have is, what CCS prediction model are you using?
So we utilized a publication that came from Professor Chu's lab in Shanghai. So this is based on a machine learning approach, and our prediction model uses 18 different lipid classes and 400 different lipids which were used as part of the training set. So we find we have excellent correlation in the most common lipids which were used as part of that training set.
Thank you. And so we have time for just one more question right now, and that is, how do you identify unknowns?
So the unknown ID is based largely on the annotation quality scoring that I showed. So that's the match with accurate mass, with retention time, with the millisigma, which is a fit of the isotopic abundances, the MS-MS score, and the CCS. Now, you can use a library. So in this presentation, I showed the rule-based annotation approach to assign MS-MS spectra to a certain lipid classification. You can also use a library-based approach. So you can use Lipid BLAST, for example. If you don't have that particular lipid within a library, then there is also an in silico fragmentation, which is built into Metaboscope, that you can use, and the same for the CCS prediction. So if you don't have a known CCS value, then for that you can predict a CCS value. But I would say it's each of those 5 aspects together, which will give you a really confident identification within your sample.
Thank you very much, Dr. Woods. We really appreciate your time today. Just to remind everybody that any questions we did not have time to get to will be sent to the speaker. And as with all the other talks in the event, this talk will now be available to view whenever you would like for the next month. And we will be back soon with the next talk.